So in the previous lecture, we were discussing direct products, right? So let's see what we discussed. So we saw that if we have a group, point group with these are my symmetry operations, and if I have xi as the linear combination which consists of various functions x1, x2, x3, and let's say xm, and another basis is yj where j varies from 1 to n, y2, y3 up to yn. If these two form the basis of the representation, then my representation would be written as certain matrices and in this case these are the characters basically, right? And if I have the direct product of this also forming, which will also form the basis of my symmetry operations, then in that case I will have another set of matrices which will form a representation, right? And I'll call this representation as tau xy. Now in this case I can always write that R, when it is operated on xi yj, then I get summation. What we get was xji and ylk, xj and yl, right? It's a double summation with j and l going to corresponding values of m and n, right? Okay, and then we also saw that we can replace this to single number because this is a product of numbers simply. So I can write this and the indices will be written as jl ik. So basically this means here is if this is my m cross m matrix, if this is my m cross m matrix and this is my n cross n matrix, what I get here is mn cross mn matrix. So Z basically represents the matrix element of mn cross mn. That is, if I have a 3 cross 3 matrix here, 2 cross 2 matrix here, the direct product matrix will be a 6 cross 6 matrix, right? So writing this and then dealing with such matrices is not straightforward and it's rather cumbersome. So what we do is we will see what is the trace of these systems. So basically here what we have shown is that the character under Z, where Z is the product of the two, so I can write it as Z, and under any symmetry operation is the product of the two characters, right? This we have seen. Now this means if these numbers are 1-digit numbers, that is 1 cross 1 representation, then the characters gets multiplied directly. But if these representations are degenerate representations, that is m-fold degenerate and n-fold degenerate, then the corresponding matrices or the corresponding characters are, we have m cross m and n cross n characters, and then we have to take a direct product of those matrices to actually get to the representation of the direct product, right? So now what we will do is we will rather work with traces and we will see why, because the working with traces actually simplifies the product here. Okay, so what we'll do is we will show here that trace of a direct product of two matrices, so which is basically here. So this is the direct product of two matrices here, this matrix, right? This set of matrices is equal to product of trace of matrices. That is very good point. Now let's say, so what we are saying here is that if we take a trace and multiply these two, what we will get is we'll get a trace of this, right? Trace is basically sum of the diagonal elements, where trace is, I can say, sum of the diagonal elements. So carrying out the multiplication of the two matrices to obtain a direct product is not as trivial, and then working with traces is much better, because we will show that trace of a direct product of two matrices, that is trace of this matrix, is equal to product of the two traces. Okay, now let's see how do we get that. Let's say mathematically what we can write. We can write this statement as trace of A cross B. Now direct product is denoted by this symbol. So this means direct product. So we are saying that the trace of direct product of two matrices, matrix A and matrix B, is equal to product of trace of A into trace of B. So now notice that this multiplication is a simple product. This is a simple product, because these are just the numbers. So numbers can always have only the simple product, whereas the two matrices have a normal matrix multiplication or a direct product, right? So this is a direct product. Okay, so now let us write the two matrix with different dimensions, just to make it general. So let's call it as 2 cross 2 matrix, or yeah, let's call it as 2 cross 2. So we'll say A11 and A12, this is equal to A21 and A22, right? And let's call another matrix, which is, let's call it as 3 cross 3 matrix. We will say B11, B12, B13, B21, B31, B22, B23, B32, B33, right? Okay, so now if we have to take the direct product, what we do is A direct product B. Now if this is 2 cross 2, if this is 3 cross 3, what we will end up is, we will end up in 6 cross 6 matrix. Okay, so that means each of this element will be multiplied by each of this element. Okay, now that gives you A11, B11, A11, B21, A11, B31. So I have multiplied A11 first. I have picked up this A11 over here, and I have multiplied with all the matrix elements here, like this. So A11, B12, A11, B13. Similarly, here we will have A11, B22, A11, B23, A11, B32, A11, B33. So on, we will get 6 cross 6 matrix. I'm not going to write the full representation here. So full matrix, but you got the point. So next element will be A21 multiplied with all 9 elements of the B matrix, right? So now if we want to calculate the trace of A cross B, A direct product B, we'll have to take all of these elements and make a summation. So that means this is A11, B11 plus A11, B22 plus A11, B33, and the right hand 6 elements, right corner, will get A, basically this multiplied by all of this. So we'll get A22, A22, B11, A22, B22 plus A22, B33. This will be the trace, because these will be the 6 elements along the diagonal, right? So now I can say that I can take A11 common from here, and what do I have here is B11 plus B22 plus B33, and I can take A22 common from here, and I get B11 B22 B33, and this is nothing but trace of B, and this is nothing but trace of B, right? And if I take trace of B common, so I get A11 plus A22 trace of B, and this is trace of A over here, so trace of A into trace of B. So now my life is easier, because if I know the trace of this and trace of this, I simply have to multiply the two numbers to get the trace of this matrix. Okay, so that's why the working with traces is much more convenient. So we'll be working with traces here. All right. Okay, so now let us take an example over here. Okay, so let's take an example of C4V, and the elements are E, C2, 2C4, 2 sigma V, and 2 sigma D. And the representations I have is A1, A2. So I'm writing the Mulliken symbols now. B1, B2, and E. Okay, let's also do some exercise of what information we can get from Mulliken symbols. So A1, that means this is one dimension, one dimension, one dimension, one dimension, and this should be two dimension. So we can write down the characters. Now, because this is 1 and 2, that means the principal axis here will be C4. So principal axis will be positive here, and the principal axis will be negative here, right? And then this we can't tell. This is C2 collinear with principal axis, and then from sigma V, we can say that this will be positive because this is A1, and this will be negative because this is A2. Similarly, positive, negative, and this also we cannot tell from Mulliken symbols. So we have to look at the notes, -1, 1, and the rest of this also we cannot tell, 0, 0, 0. Okay, but we could still fill a lot of character table by just looking at the Mulliken symbols, right? So now let's say if we take a representation for where we have direct product of A1 and A2. So we can write down the product of the two traces, and we will get 1, 1, 1, minus 1, minus 1. Let's take another example. Let's say if we obtain a direct product of B1 and E. So what do we get? 2, minus 2, and then we have 0, 0, 0, because these are all zeros, right? We can also do a direct product with self IR. So E cross E will be equal to 4, 4, 0, 0, 0. Okay. Now whether this A1 and A2 is reducible or irreducible, that you can always use great orthogonality theorem to find out if a representation obtained by the direct product of two IR representations is reducible or irreducible. Okay, so for example, if we say A1, A2, this we can directly see that it's a irreducible representation, right? Because it is composed of only A2. Similarly, B1E, we can say that this is also an irreducible representation because it is only composed of E. E square, however, we can say that it does not belong to any of this, so it has to be a reducible representation. And we can also test it. So for E square, for example, we can say sum of squares of characters, it is 4 square plus 4 square plus 0 square plus 0 square plus 0 square. This is equal to 32, whereas our H is 1, 2, 3, 4, 5, 6, 7, 8, right? So since these two numbers are not matching, that means E square is a reducible representation. So that should be very easy to find out. Okay, so now how do we find out the components, what constitute E square? So we can do that also. So E cross E is equal to, we can say A1, A1, A2, A2, A3, B1, A4, B2, and A5, E, right? So remember the reduction formula which we used. So Aj is equal to 1 over H summation over all R chi R and chi JR, right? So this was the reduction formula which we derived earlier. So where this is the character under reducible representation, this is the character under irreducible representation, and we can actually find out all the A's corresponding to this. So let us see for this, we'll work it out. So for A1, let's say 1 over 8, and we will have, so this will be 1 into 4 plus 1 into 4. So what I'm doing is I'm making a product of 1 into 4 plus 1 into 4 plus whatever product, does not matter because it's all 0. So this will be 4 plus 4, 8. So this will be 1. So that means there will be A1 component present. Okay. So let's do for A2. So A2 will be 1 over 8, 1 into 4 plus 1 into 4 plus again this will be odd 0. So we will have at least one A2 present. Okay. So let's move forward. For A3, we have to now multiply with B1 characters. So 1 over 8. And doing the same thing, what we will get 1. I have not done the complete calculation here, but what we will get is 1. And A4 also we will get 1, and we can see that A5 will be 0. So this implies that E direct product E will be equal to A1 plus A2 plus B1 plus B2, and that's all, right? So we can see this. So if we make a sum of this, 1 plus 1 plus 1 plus 1 equal to 4, and then again 4. Now 1 plus 1 minus 1 minus 1, 0. Again there are 2 positives, 2 negatives, so 0. 2 positives, 2 negatives, so 0, right? So it's very clear that this is a reducible representation and it gets reduced to A1 plus A2 and B1 plus B2, right? Okay. So that is also very clear. So we can say here that usually direct product of 2 or more IR representations will be a reducible representation. So I use the word usually here because there are exceptions. Exceptions are if you are multiplying totally symmetric representation into any IR, what you will get is that same IR back. Because totally symmetric representation is all ones, so multiplying anything with all ones will not change anything, and then you will get the same IR back. That is very easy to see, right? Okay, so let's also see few more or one more rule. So this is a rather important rule, so pay attention to this. In a direct product of an IR with itself, the totally symmetric representation, I'm not saying it as A or A1 because in different point groups, the nomenclature or monical symbol for totally symmetric representations can be different. Somewhere it can be A, somewhere it can be A1, and so on, right? But it will always be A or A1 or something similar to that. But here we will use the general term totally symmetric representation. IR occurs exactly once. So if we take the direct product of an IR with itself, like we took direct product of E with E here in this example over here, so we saw that A1 comes only once, right? So that is the totally symmetric representation will definitely come, and it will come only for one time. Okay. So totally symmetric representation occurs exactly once, and we will also see that we'll show both of these in one go. So I'm just writing it together. In a direct product of two different IRs, the totally symmetric representation never occurs. So that means in the product above, if we see here, in for example, we did this B1E. So B1E, this is the product of two different IR representations. And in this case, B1E is actually equal to only E, right? So there is no other representation. So that means in B1E, this will never occur. So similarly, if we do A2 into B1 or A2 into B2 or A2 into E or B1E or B2E, in any of these direct products, A1 will never come. That's what it says. And if we do self product, A1 will come and it will come exactly for once, right? So this is what it says, that in a direct product of two different IRs, the totally symmetric representation never occurs. So let's try to see. Let's try to prove it. Let tau I be an IR of a group of order H. So what I mean here is that if we have a group of order H, let's call it as GH, then I can say that this is E, R2, R3, and up to RH, right? So I'm not classifying these as different classes. I'm just writing R1, R2, R3, R4, RH, and R1 I'm simply writing as E. So let's say I have a tau 1, which is the totally symmetric representation. So I'll have all ones here. And I have a general IR, which is tau I. Okay. So that means here it will be Li, which is the dimension of this. It can be 1 or anything. And then I'll have different characters or matrices depending on the dimension of this. R2, R3, and so on, RH. Now, if I do a direct product of tau I into tau I, what do I get? I get Li square, then I get R2 square, R3 square, RH square, right? So here, now if I want to find out the component IRs of this then I can say that AI is equal to 1 over h summation over all r. This is directly from reduction formula. So this is character under direct product, and this is the character for the corresponding irreducible representation, right? So for totally symmetric representation, if we want to find out what is the component for totally symmetric representation, we can say that this will be A1 and this will be tau 1 here. So I can say that A1 is equal to 1 over h summation over all r chi AB over r, and this will be character under any symmetry operation, corresponding symmetry operation, which will be actually 1, right? So that product is not to be written there because this will be 1. It will always, for all r's, it will be always 1. So this implies that I can write my character as chi A r chi B r, right? So I can always use this equation here. So A1 is equal to 1 over h summation over all r A r, where A and B are two irreducible representations, right? So that means I can say that from great orthogonality theorem, I can say that this is 1 over h into h delta A, right? So summation over all r character of two IR representations gives you delta. We have learned this in terms of chi I, chi j, and this will be delta ij. Remember? So this is directly from GOT properties. So if you go back and look at the lectures where properties, 5 properties of GOT were discussed, we had discussed this one. So that means now h is cancelled here. So this is basically delta AB. So A1 is nothing but delta AB. So now we can say that if A is equal to B, then A1 is equal to 1, and if A is not equal to B, A1 is equal to 0. So now here we have shown the first case which we wanted to show. If in the direct product of an IR representation with itself, where A will be equal to B basically, so A1 is equal to 1. A1 means the totally symmetric representation will come only once, and it will always come, it will come only once. If the direct product is of two different IR representations, then A1, or that is the totally symmetric representation, will never come, right? So that is also easy to see. All right. So I think that is all for this lecture, and now next class we will see how do we use direct products. Okay. So those examples we'll see what is the actual application of direct products in solving some problems of quantum mechanics, that we will see in next class. All right. Thank you.